So today, no new concepts, no new ideas. We can relax a little bit. And I want to discuss with you the connection between electric potential and electric fields. Imagine I have an electric field here in space, and that I take a charge Q in my pocket, I start at position A, and I walk around, and I return at that point A. Since these forces are conservative forces, if the electric field is a static electric field, there are no moving charges, but that becomes more difficult, then the forces are conservative forces, and so the work that I do when I march around and coming back at point A must be 0. It's clear when you look at the equation number 3 that the potential difference between point A and point A is obviously 0. I start at point A and I end at point A, and that is the integral in going from A back to point A of E dot dl, and that then has to be 0. And we normally indicate such an integral with a circle, which means you end up where you started. This is a line now. This is not a closed surface, as we had in equation 1. This is a closed line. And so whenever we deal with static electric fields, we can add now another equation if we like that, and that is if we have a closed line of E dot dl, so we end up where we started, that then has to become 0. Later in the course we will see that there are special situations when we don't deal with static fields, when we don't have conservative E fields, that is not the case anymore. But for now, it is. So if we know the electric fields everywhere, then you can see equation number 2, then we know the potential everywhere. And so if we turn it the other way around, if we knew the potential everywhere, you want to know what the electric field is. And that, of course, is possible. If you look at equation 2 and 3, you see that the potential is the integral of the electric field. So it is obvious that the field must be the derivative of the potential. Now, when you have fields being derivative of potentials, you always have to worry about plus and minus signs. Whether you have to pay MIT $27,000 tuition to be here, or whether MIT pays you $27,000 tuition for coming here, is only a difference of a minus sign, but it's a big difference, of course. And so let's work this out in some detail. I have here a charge plus Q, and at a distance r, at that location P, we know what the electric field is. We've done that a zillion times. This is the unit vector in the direction from Q to that point, and we know that the electric field is pointing away from that charge, and we know that the electric field E, we've seen that already the first lecture, is Q divided by 4 pi epsilon 0 r squared in the direction of r roof. And last lecture, we derived what the electric potential is at that location. The electric potential is Q divided by 4 pi epsilon 0 r. This is a vector. This is a scalar. So, the potential is the integral of the electric field along a line, and now I want to try whether the electric field can be written as the derivative of the potential. So let us take the VDR, and let's see what we get. If I take this dVdr, I get a minus Q divided by 4 pi epsilon 0 r squared. Of course, if I want to know what the electric field is, I need a vector. So I will multiply both sides, which is completely legal. There's nothing illegal about that, with a unit vector in the direction r. So that turns them into vectors. And now you see that I'm almost there. This is almost the same, except for a minus sign. And so the derivative of the potential is minus E, not plus E. And so I will write that down here, that E equals minus dV dr.